So in this simplest example, you're going to dissolve an acid in water and see what happens. So once I say see what happens, you could be asked like, what's the concentration of the acid and the base, and what's the pH of the solution? Now, when we talk about concentrations, when we do our calculations, we're typically going to be doing these in molarity. So this is going to be typically in terms of molarity. We'll see later that we might have to work in terms of moles for some of the problems if we need to consider a changing volume. But for these simpler ones, we're not going to worry about that, and we're just going to be dealing with in terms of molarity. And then if you're given the volume, you can calculate actual moles. Okay, and then the pH of the solution. So the pH is going to depend on the proton concentration, which is going to be one of those products from the reaction. So let's go ahead and sketch out what this reaction is actually going to be. So we're going to start, and we're going to have our acid. And we're going to take our acid. What color should I be? Okay, so we're going to take our acid. We have some acid, we have HA. Remember, that's just our generic acid. And we're going to go ahead and we're going to add it to water. Now, some of it's going to deprotonate, and that's going to give us our conjugate base, as well as that proton, which is going to grab onto a water and give us this hydronium ion. And this is going to be a reversible reaction, so it's going to be going back and forth in each direction, and it's going to equilibrate over time. So give time, and we'll equilibrate. So it's going to find its happy place, and its happy place is going to be characterized by its Ka, or we can also think of it as by its pKa. Remember, the pKa is just going to be the negative log of that Ka. So what's happening when this acid dissolves? Well, we're going to be losing some amount of the acid. So some quantity of the acid is going to be dissociating. And we can represent this, no matter, we don't know what it is right now. Right now, we're just talking in generic terms, but we can represent it as some variable X. So some variable X is going to get removed. And that when you lose X amount of the acid, well, now you're going to gain X amount of the base, the conjugate base. And you're also going to gain X amount of that hydronium ion because you've basically lost it, given it to a water, and given it to make this H3O plus. So now technically this is going to take away a water molecule. But the thing is, we're just going to ignore the water. Because the water is such a high concentration, we're just going to ignore, and we're going to take it as a constant. And we're going to take it as a constant that's going to be kind of accounted for in all of our calculations, so we don't need to worry about this. And so why is this a valid thing to take as a constant? Well, if you think about the water concentration in cells, or water concentration in water, it's basically like 55.5 molar or so. So this is going to be super high concentration. And we'll see that when we do these equations, they're only even going to be valid at dilute solutions. So we're not going to be talking about anything that's even like a molar. That would be a high concentration considered. And we have water is going to be about 55.5 molar. So anything we do to change that water concentration is going to just be a drop in the bucket. And so we're not going to worry about it. And so for now on, we're just going to simplify this reaction as thinking about it as HA dissociating to give you A minus plus H3O plus. Okay, so that's going to be our equilibrium reaction. And remember, for any reaction that's at equilibrium, we can write a KEQ equation. So we can go ahead and write a KEQ equation, which is equal to our products over our reactants. And in this case, that would be our A minus, or conjugate base, times our proton concentration all over our HA. So this is our equilibrium constant. And remember that in the case of an acid dissociation, this is also equal to our Ka. So we can say that the Ka is going to equal concentration A minus H3O plus all over HA. Okay, so we can write this equation. And now what we're going to do is we're going to plug in these changes, these X variables that we got. And so I'm going to kind of clean up the page a little. So now that we're ignoring the water, let's go ahead and let's rewrite this equation over here. Let's rewrite our A and that sort of thing. Okay, so we have HA over here, A minus plus H3O plus. Now, the first time we're actually going to do this, let's go ahead and let's do an ice table so you can help see where things come from. And then we'll see how we can kind of skip the ice table if we recognize the trends. But then later we'll come back to our ice tables. So if we think about our initial concentrations, if we have our HA, we're going to be given this. Typically, I'm talking about like the typical situation. You could have all sorts of variations of this, but typically you're given that HA concentration because you're dissolving some amount of acid. And when you dissolve it, you're going to get some amount of your base and some amount of the protons or the hydronium ions, but you're starting with 0. So these are going to be 0. So you have your 0 initial, which is going to make things easier in this case. Now what's going to happen is you're going to have some sort of change to your system. And so in this case, what our change in the system is we're going to have X amount deprotonate, which is going to leave us with that same amount of the conjugate base and that amount of the proton, of the hydronium. So these are going to be positive. We're gaining these and we're losing that amount of the acid. And so now at equilibrium, what we're going to be left with is we're going to have our equilibrium is going to be the given acid concentration minus X. And this is going to be plus X and plus X. And so now what we can do is we can say that, well, we have, this is going to be our equilibrium concentrations, and the Ka, well, that is going to be using the equilibrium equations. So what we can do now is we can do plug into here. So now what we can do is we can take that Ka equation and we can say, okay, so Ka is going to be equal to our conjugate base concentration, which we said is X, times our hydronium concentration, which is also X. And that's all going to be divided by your given acid concentration minus X. And so what you're going to have is this is going to equal to X squared over the given acid concentration minus X. And so we can then do this equation when we have the pKa by recognizing the relationship between the Ka and the pKa. So remember that we can get the Ka is also going to equal 10 to the minus pKa, and that is going to equal our X squared over our given acid concentration minus X. And so in order to actually solve these equations, we're going to have to use the quadratic formula. And I don't know about you, but I am not going to want to use write out a quadratic formula and figure out those solutions if I don't have to. So I'm not going to require that my students do the quadratic equation on paper or something like that. I'm going to go ahead and use Wolfram Alpha. And you can use whatever works for you and your teacher if you're watching this from a different class. But that's going to give you 2 solutions. Only one of them is actually going to be plausible. And so you'll have to determine which one's going to be plausible. Sometimes it'll be easy because one of them is negative. In other cases, what you'll have to do is you'll have to think about the limiting concentration and make sure that your value is going to not be more than the amount that you actually have to start with. Okay, so now let's do an actual example. So how much acetate forms when 150 millimolars worth of acetic acid is dissolved in water, and what is the pH of the resulting solution? So we're starting with 150 millimolars of acetic acid. So that's going to be our initial. So what we can say is if we go ahead and write out that ice table, and remember that if you don't need the ice table, feel free to skip it if you don't feel like you need it, and go straight to what we were talking about before with this equation. But for now, let's just write it out in full so that we can really see where things are coming from. So we're going to have this reaction where instead of our generic and acid and base, we're now going to be talking about having this acetic acid, and it's going to be dissociating into its acetate and the hydronium ion. So if we think about our initial concentration of this, well, we're given that our concentration of our acid is going to be 0.150, because we want to be in molarity and not in millimolars. And then we're going to have our initial concentrations of these are going to be 0. But they're not going to be 0 for long because some of our acid is going to dissociate. X amount is going to dissociate, leaving us with X amount of our conjugate base and X amount of our proton or our hydronium. So our final, once it reaches equilibrium, is going to be 0.150 minus X, X, X. And now we're going to plug those into our Ka equation. And so if we take our Ka, in this case, it's going to be equal to our X from here. So our X from the acetate times the X from the hydronium over this 0.150 minus X. And remember that our Ka, we're not given the Ka, but we are given the pKa. And so in this case, we're given that the pKa is equal to 4.8. And so remember that instead of thinking of this in terms of Ka, if we want to think about this in terms of the pKa, that would be 10 to the minus pKa. And now we can simplify this and put in some actual numbers. So I'm just going to put the, you can do basically X squared over 0.150 minus X equals 10 to the minus 4.8. And now I'm just going to go ahead and I'm going to plug this into my Wolfram alpha and see what it gives me for X. Remember to look and make sure that you have all the your parentheses and stuff that's needed so that it gives you the right answer. Thankfully with Wolfram alpha, it's really nice in that it'll kind of like show you the formatted version. So you can check and make sure you're actually written what it actually thinks you wrote, what you meant to write. In this case, it's going to give me 2 solutions. So it's always going to give you 2 solutions to a quadratic equation. So in one of them, the solution is going to be minus 0.0015. Or the X is going to be equal to 0.0015. And I'm rounding, so it actually goes a little more. So if you want to think, these are actually, they are different numbers. So this one would be like 155, and this one would be 153. And again, if you rounded earlier, you get a slightly different answer as well. But let's think about which of these answers is correct. So it's going to give you 2 answers, but only one of them is ever going to be accurate. In this case, one of our numbers is negative. Can we have a negative number? Can we have a negative amount of something? No. Unless, I don't know, are you talking about like dark matter or stuff like that? I don't know. This is not that sort of thing. Instead, it's just a wrong answer. So we can ignore it. And this means that this is our right answer. So right now, we're not in the context of units, but we need to go ahead and think back to what this 0.00153 actually represents. We're talking in terms of concentrations, and here we're talking about our molar concentrations. And so our concentration of our acetate is going to be equal to X, and our X is equal to 0.00153 molar. And let's go ahead and in order to kind of compare it to the amount of acid, let's go ahead and let's think about it in millimolars. If we want to think about it in millimolars, well, we're going to multiply by 1,000, 1, 2, 3 moves of our decimal point, and we're going to get 1.53 millimolar. Okay, so now anytime you do an equation like this, I want you to stop and think about whether the answer is reasonable. So going into this, what would we expect? We have that our pKa of acetic acid is going to be 4.8. This is going to be a relatively weak acid. If something is a weak acid, we wouldn't expect that much of it to be deprotonated if you were to just stick it in water. And in fact, the Ka is going to tell us about how much would get deprotonated if we were to just dissolve it. And when we figured out our Ka, we kind of didn't do it explicitly, but let's go ahead and do that now. Instead of just saying 10 to the minus 4.8, let's go ahead and let's see what this is. So Ka equals 10 to the minus 4.8. And if we do 10 to the minus 4.8, we get 0.1234158. So really, really small. Really small. And what does this mean? This means that not very much of it is going to be dissociated. And so because it's going to tell us that basically our reactants are much favored over our product. So the acid, this bottom part of the equation is going to be much bigger than the top. So we get a really, really small number. We have a lot of, less of it is going to be dissociated. And so if we compare our concentration of our acetate, so 1.53 millimolar, to our concentration of our acetic acid, 150 millimolar, well, now we can see that, yes, this is a lot smaller. This makes sense. So we're about 100 times smaller, 100 times less of our base. So this is all making sense. But we're not done with the problem. We still have the extra question of what is the pH of the resulting solution? And in order to solve the pH problem, we need to know the proton concentration. And thankfully, the proton concentration, we have that as well. So our proton concentration, our hydronium concentration, is going to be equal to X. So we can use this to calculate the pH. And so here, what we're going to be doing is we're going to, I don't want to erase that because we're still going to need that X. We have the same X, but now instead of the Ka and the pKa, we're going to be dealing with the H3O plus and our pH. So we have our pH is going to be equal to log of 1 over X, which is going to be the same as saying 1 over 0.00153. And if you plug this in, then you get that your pH is going to be equal to 2.82. So our pH is going to be 2.82. And we're going to have 0.00153 molar concentration of our acetate and of our protons. So remember that it's this concentration of protons that's going to then be determining the pH. And our pH in this case is going to be 2.82. Okay, just a note that you can also write this as pH equals the minus log of your H3O plus. So it's just a little different ways you can write it mathematically, but both of those would give you the same answer.